In the last lecture, we saw the detection of the SSB SC modulated signal by using synchronous or coherent detector. There are three cases. In the first case, the carrier signal from the local oscillator has a phase shift of 0 degree and an amplitude of 1. This was the ideal case. In the second case, the carrier signal from the local oscillator has a phase shift of phi and an amplitude of 1. And today we are going to discuss the detection of the SSB SC modulated signal where the carrier signal from the local oscillator has a frequency shift of del f and an amplitude of 1. We have already discussed second case of the detection of the SSB SC modulated signal. In this lecture, we will discuss the third case of the SSB SC modulated signal detection. In order to understand this properly, you need to watch the two previous lectures for the detection of the SSB SC modulated signal. Click on the I button and go to the link for watching the lecture. Now we will see the case where the carrier signal has a frequency shift of del f. The block diagram remains pretty much the same as the first case. Instead of having the carrier signal with the frequency f, now we will have a carrier signal from the local oscillator which has a frequency f and a frequency shift of del f. Let's see the mathematical analysis for the detection of the SSB SC modulated signal with the frequency shift of del f. Let's say SSB SC modulated signal st is equal to AC by 2 into mt into cos omega ct plus minus m cap of t into sin omega ct. And the carrier signal having the frequency shift del f can be given by ct is equal to cos 2 pi fc plus del f into t. Then the output of the product modulator yt is equal to st into ct. Now if we replace the value of st and ct in the equation of yt, then yt becomes yt is equal to AC by 2 into mt into cos omega ct plus minus m cap of t into sin omega ct into cos 2 pi fc plus del f into t. Now we will multiply this cos 2 pi fc plus del f into t with both the terms, then yt can be written as yt is equal to AC by 2 mt into cos 2 pi fct into cos 2 pi fc plus del f into t plus minus AC by 2 into m cap of t into sin 2 pi fct into cos 2 pi fc plus del f into t. Now we will divide and multiply this equation by 2, then yt can be written as yt is equal to AC by 4 into 2 into mt into cos 2 pi fct into cos 2 pi fc plus del f into t plus minus AC by 4 into 2 into m cap of t into sin 2 pi fct into cos 2 pi fc plus del f into t. This equation can be reorganized as this. Now we will take AC by 4 into mt common from both the terms, then yt can be written as yt is equal to AC by 4 into mt into 2 into cos 2 pi fct into cos 2 pi fc plus del f into t plus minus sin 2 pi fct into cos 2 pi fc plus del f into t. Now we know that 2 cos a cos b is equal to cos a plus b plus cos a minus b, and 2 sin b cos a is equal to sin a plus b minus sin a minus b. If we apply both of the formula, then this equation of yt can be written as yt is equal to AC by 4 into mt into cos 2 pi fc plus del f into t plus cos 2 pi fc minus fc minus del f into t, and plus minus AC by 4 into m cap of t sin 2 pi fc plus del f plus fc into t minus sin 2 pi fc plus del f minus fc into t. After simplification, yt can be written as yt is equal to AC by 4 into mt cos 2 pi into 2fc plus del f into t plus cos 2 pi minus del f into t plus minus AC by 4 into m cap of t sin 2 pi 2fc plus del f into t minus sin 2 pi del f into t. Now we know that cos minus theta is equal to cos theta. If we apply this formula here in this equation, then cos 2 pi minus del f into t will become cos 2 pi del f into t. Now we need to multiply AC by 4 into mt with both the terms, then the equation can be written as AC by 4 into mt into cos 2 pi 2fc plus del f into t plus AC by 4 into mt into cos 2 pi del f into t plus minus AC by 4 into m cap of t sin 2 pi 2fc plus del f into t minus AC by 4 into m cap of t sin 2 pi del f into t. This output is passed through a low-pass filter which does not allow the high-frequency terms, or it attenuates them and only allowing the low-frequency terms to pass through. Here, AC by 4 into nt into cos 2 pi del f into t is the message signal multiplied by a constant of AC by 4 and cos 2 pi del f into t. And AC by 4 into mt into cos 2 pi 2fc plus del f into t is the message signal multiplied by a constant of AC by 4 and a high frequency term of cos 2 pi into 2fc plus del f into t. And AC by 4 into m cap of t sin 2 pi fc plus del f into t is the Hilbert transform message signal multiplied by a constant of AC by 4 and sin 2 pi del f into t. And finally, AC by 4 into m cap of t into sine 2 pi f del f into t. It is the Hilbert transform of SS signal multiplied by a constant of AC by 4 and of sine 2 pi 2fc plus del f into t. Here, the two high frequency term or AC by 4 into mt into cos 2 pi 2fc plus del f into t and AC by 4 into m cap of t into sine 2 pi 2fc plus del f into t will be eliminated due to the low pass filter. So output of the low pass filter or y naught t is equal to AC by 4 into mt into cos 2 pi del f into t plus minus AC by 4 into m cap of t into sine 2 pi del f into t. This above equation yields a fascinating outcome as it demonstrates that y naught t is completely distinct from mt. Contrary to the initial assumption, y naught t actually represents an SSB SC modulated signal where mt serves as the modulating signal and del f functions as the carrier signal. From this equation, it is clear that when del f is close to 0, then sine 2 pi del f into t is equal to 0 and cos 2 pi del f into t is equal to 1. And y naught t is approximately proportional to mt. In reality, a frequency error exceeding a few hertz leads to levels of distortion in the output of the coherent detector that are considered unacceptable. To mitigate this issue, a pilot carrier at a low power level is sometimes included in the SSB SC signal prior to transmission. At the receiving end, a technique known as homodyne detection is employed. In the case of speech signal, this does not result in significant distortion as long as del f remains within the range of approximately plus minus 10 Hz. When it comes to music, any frequency translation affecting all the frequency components will lead to a significant distortion. Therefore, even if the del f is within the range of plus minus 10 Hz, it will still be considered unacceptable due to the severe distortion it introduces. In the case of video signal, no energy gap will be present. Consequently, the detected signal will be a highly distorted re-addition of the original modulating signal mt. Such distortion is completely intolerable and cannot be accepted under any circumstances. This concludes our discussion for this lecture. In the event that you have any question regarding this presentation, feel free to post them in the comment section and don't forget to hit the subscribe button. See you in the next one.